All right, so today I'm going to talk about refraction, okay, and what refraction is and how we interact with it on a daily basis, and why we see light sometimes bend in certain ways. We obviously know that light doesn't bend, that light travels in a straight line, okay, but as light travels through specific medium, and remember how we spoke about medium earlier on in the unit, being being substances in which can transmit light, okay. Um, you can either you can change the speed of that light based on that medium, and we'll talk a little bit about that today. But the first thing is I really want to talk about is what exactly refraction is. Okay, so refraction is the bending or change in direction of light when it travels from one medium to another. Okay, so when light travels from, let's say, air, which is here, okay, into a glass of water, okay, what happens is that it slows down and interacts with the waves of the light, okay, and bends the light because it's slowing down, okay, and it bends the light. It actually slows down those wavelengths a little bit, causing the light to bend. And we see this in a number of different examples throughout our everyday life. I don't know if anyone's ever put a spoon in a glass or a pencil in a glass, and it kind of looks like the pencil or the spoon bends. That's because of the light rays moving from the water, okay, hit the air and they change speed, and the light waves change speed, and you actually see it a little differently. Maybe someone has seen something like this, where they put a straw in there and it kind of bends that way. Not only is the water playing an effect on our eyes on this in this situation, but the actual glass itself, its curvature, it's glass, so it interacts with light waves as well, can also cause that effect too. Okay, but that's something that you would see in a glass for sure. Another thing here, this one. Okay, this one looks pretty crazy, right? But again, it is the combination of the glass and the water that is causing this to happen. As the light rays reflect off of this guy's body, okay, it's coming, hitting with the water, it's interacting with the water at a lot slower pace, interacts with the glass even slower than water, and then comes to our eyes through the air, which is a lot faster. So light rays can travel a lot faster in air. Okay, so refraction is caused by a change in the speed of light as it travels through different materials. Okay, we know that the speed of light in a vacuum is the fastest thing that we have in physics. Okay, that we know as that we know in physics. Okay, light again can travel through a complete vacuum, and it's the only wavelength, electromagnetic wave, are the only wavelengths that can travel through a vacuum, and we know that light travels at 3.00 times 10 to the 8th meters per second. Okay, and if we compare that speed to the speed of light in water, it's still super duper fast, but it's just not as fast. Okay, so the speed of light in water travels at 2.26 times 10 to the 8 meters per second. And then speed of light in acrylic is 1.76 times 10 to the 8th meters per second. These are obviously still really fast, okay, but compared to the vacuum, it is a lot slower. Okay, and you can think of refraction as if you were pushing uh, a wagon from pavement onto sand. Okay, and you would expect that wagon would slow down when it hits the sand, right? Because it's not rolling as good. Okay, so what happens if you push this wagon on an angle towards the sand? Okay, so you have your incident angle. Okay, is this front tire is going to hit the sand first? So this front tire hits the sand first, and you can see that the other three tires are still moving at the speed of the wagon on the pavement. Okay, this one slows down, so what's going to happen is this is going to bend and turn as it pushes into the sand. Okay, and that's kind of the idea of refraction. Okay, is that part of the light beam interacts with the other material, the other media first, and slows it down and kind of bends it, similar to that of a wagon. Okay, one, two, three wheels will continue traveling at the speed that the wagon was going on the pavement, while the one wheel that's on the sand is now slowed down, and it's causing the wagon to bend away from that original trajectory um, through the sand. Okay, this is obviously resulting in a change in direction. Um, so we can take a look at that through this little visual here. Let me change my screen here. So we have our laser, we can call this air, we can call this water. And what's going to happen is, you have your light beam from the air. okay, going into the water, and it actually bends when it hits the water. We can move this laser up or down, and if you move it completely directly above the normal, so it's going perpendicular to the media change. So we have air and water, and this is the line at which the media changes. You won't have any refraction. You also see in this instance a reflected ray, and we'll talk a little bit more about reflected rays and refraction in a little bit, okay? But that's basically what refraction is. Okay, so this would be a refraction ray diagram. Let me just move this down again. Okay, this is a refraction ray diagram. This is a refraction rate diagram for the third time. And this is what it looks like, right? You have your incident ray, similar to you would have an incident ray in a mirror. You have your normal, okay, which is similar to your plane mirror reflection as well. You have your angle of incidence, which again is similar to your plane mirror diagram as well. Okay, and then you have this line right here, and this line is the line at which you change from one medium to another medium. In this case, we can call this air up here, and we can call this water down here. Okay, and this is the line that separates that. You have your incident ray that hits that line of medium change. Okay, and it causes the light to bend. Okay, so we have our incident ray, we have our normal, then we have a refracted ray, we have our angle of refraction, and then you also have your normal. Okay, your normal will continue down through both medium at the point at which it transfers from one medium to another medium. Okay, so it's very similar to this component as to the plane mirror. All we're adding really to our refraction is an angle of refraction, okay, and a refracted ray instead of a reflected ray. Okay, we're looking at a refracted ray, okay, and you have an angle of refraction. So there are a couple rules when we look at of refraction. Okay, the first one is the incident ray and the refracted ray and the normal all lie within the same plane. Okay, we talked about planes earlier on. Okay, and they all lay within the same plane. The incident ray and the refracted ray are on opposite sides of the line that separates the two medium. Okay, if we go back here, you have your incident ray. It's on the one side of the line that separates the two media, and then you have your refracted ray, which is also on the other side of the line um, that separates the two medium. I feel like that's pretty explanatory. Okay, in a mirror, we had them lay on the same plane, but they reflected instead of refracted. Okay, reflected instead of refracted, refraction, reflection. Okay, just give you an idea here. The third rule, okay, is if light is traveling from a less dense medium to a more dense medium, the light rays will bend towards the normal. So if I go from water to glass, we know that water is less dense than glass, okay, or say air to water. Okay, we know that water is less dense than grass. What's going to happen is this light ray is going to hit here, okay, and then it's going to bend toward the normal, okay, and we have our normal right here. And the normal is drawn in a perpendicular line to the line that separates the two medium. Okay, so from less dense to more dense, you're going to bend towards the normal, and from more dense to less dense, you're going to bend away from the normal. Okay, in this case, we have air and water. We have our incident ray traveling from the water up, hitting the normal at an angle, and then you have your light ray bending this way, away from the normal. Okay, so my angle of incidence is less than my angle of refraction in this case. So again, those are two things that you're going to need to really to know moving forward. Okay, in this case, this is exactly what I'm showing here is as light passes from air to glass, what happens is light travels at an angle to that glass, and your angle of incidence is going to be greater than your angle of refraction. If I were to draw another normal right here, where this incident ray, transfers from glass to air, my normal's here, and I can see that my angle of incidence, which would be right here, okay, from here to here, let's say I drew that, is less than my angle of refraction, okay? So just to keep that in mind. the more dense a material, from going from less dense to more dense, you're going to bend towards, and then from more dense to less dense, you're going to bend away. Okay, and this interaction of light is what allows us to see the different colors in the visible light spectrum. Okay, we have a white light beam interacting with the glass prism here, and the glass prism bends and slows down the white light to different wavelengths, and those different wavelengths are visible light that we can see through the visible light spectrum. Okay, another example that you might interact with or see is if you were to look at an angle. So this was you're looking at an angle at a glass of water with a pencil in it. Okay, the pencil appears bent in the glass of water because the light reflecting off the pencil bends as it travels from water to air. Okay, and remember what we said, right? We said from a more dense material to a less dense material, what's going to happen is it's going to bend away from the normal. So we can picture our normal right here. Let's just picture that right here. Okay, and light rays are traveling, hits the line at which separates the two media, and our normal, okay, and this is our normal right here, okay, and we can see that the light bends away from the normal and to our eyes, okay. If we were to extend these rays back into the water, we would actually perceive the pencil to be over here instead of over here. It's because the light rays then speed up as it travels from the water to the air, causing that illusion. If you were to move this eyeball, say up here, you would probably see it a little bit more real, if that makes sense, more correct. There wouldn't be any bending because you're now perpendicular to you're now parallel to the normal. Okay, you're right above the normal. So our brains think that the pencil is bending or is behind where it actually is because light bends away from the normal. Same thing happens with the penny, right? We see the penny coming up, hitting the surface of the water. Okay, and as the light travels from the water to the air, what happens is it bends away from the normal. Okay, and we can extend that refracted ray back into the water. Okay, as our eyesight, and we can see that the penny would be away or not where it actually is. Okay, and again, that's just a change of speed of light from one media to another media. Um, yeah, okay, and then we have a partial reflection and refraction. So if a surface that transmit light is very smooth, it will not only refract light, but it will reflect light. And if you remember from that demo, okay, I showed you, we saw a little bit of reflected light as well. Okay, this is a result. This is that the result is that you can see through the object, but you can also see images being reflected on the surface of the material. Okay, for example, if you ever look at a pond or a lake and it's really, really calm and really still, you can see the fish or rocks underneath the water, but you can also see the reflection of, say, trees. Another example of this would be double-sided windows on a building. Okay, in some angles you can see that there is reflection of the sky, but at that same angle you could potentially see inside the building as well. Okay, and that is because sometimes if this surface is really, really smooth, again, you can see reflections. If you're sitting near a window, okay, I'm sitting near my office window right now, and I can see directly outside, but I can also see a vase that my wife has here as decoration in the reflection of the window because I am at an angle to that window. Okay, so I obviously have some sort of reflected rays occurring there as well. Okay, so that's yeah, and that's how we get the partial reflection and refraction. I want you to take a look at page 519, number 1 to 7. You can read a little bit more about refraction on page 515. Okay, you can read a little bit more about refraction on 515 and then do the questions on 519. If you guys have any questions, just let me know.